Welcome everyone again to my course. In today's class, we will continue our discussion on LTL based property encoding, right? Specifically today we will try to see various properties which are basically equivalent in LTL, and also we will try to find out the adequate set in LTL and also few more encoding examples. If you recollect, in LTL we have four temporal operator. We have F, which is basically future or eventual. Then you have next, X, you have until, and you have global. Right? So these are the four temporal operator, and you have Boolean operator like and, or, implication, and negation. Right? So you have these four sets. We have already discussed about the semantics and syntax of LTL. So today what we will see a few examples of property whether they are equivalent or not, right? And then following we will discuss the other thing. Let us take first this. We have in eventually or future phi 1 or phi 2, and then I am saying f phi 1 or f phi 2, right? So I am basically distributing the eventual operator or future operator to the or. So are they equivalent, right? So this is what we have to see logically. So if you try to see, if I say path pi, which is say S1, S2, S3, S4 and so on. So this is my pi. I'll say if it is this in future phi 1 or phi 2 is holding, right? So if you have a scenario where say I have only phi 1 holds here, I'll say yes, this pi satisfies f of phi 1 or phi 2, right? Now if you think about the state where I want to see this, so does this hold here? Because if you have to hold this one, either this holds or this holds, right? Because phi 1 holds here, I can also say that pi satisfy f of phi 1, right? So because this is satisfying, so I can also write this pi satisfy f1 phi 1 or f of phi 2, because this is already satisfying. Similarly, if I think about let's say in the same state, say phi 2 holds here, right? Then also I and say this is not there, right? So I have this, so I can also say that this pi satisfy, this path satisfy f of phi 1 or phi 2, because there is a future state where phi 2 holds, so that means phi 1 or phi 2 holds. Similarly, in this pi satisfy f of phi 2, because in this path in future phi 2 holds, and this implies pi also satisfy f of phi 1 or f of phi 2, right? So therefore this is equivalent. So this eventual operator distributes over OR operator. Now let us see for this AND. Now let us concentrate on the AND operator and the future operator, right? So we'll try to see whether this eventual operator distributes over AND operator or not. So I'll just check whether this is equivalent or not. So this is, let us see. So if you think about a path like this, pi, and if you have some state where pi 1 holds and some state pi 2 holds, right? So some s pi. So then in this path I can say this pi satisfy f of phi 1, right? Because in some future state phi 1 holds. Similarly, pi satisfy f of phi 2, because in some future state phi 2 holds. But does this path satisfy future of phi 1 and phi 2? No, because to satisfy phi 1 and phi 2, f of phi 1 and phi 2, there should be some state where both phi 1 and phi 2 both should hold, right? Which is not the case here, right? So I'll say this path pi does not satisfy f of phi 1 and phi 2, right? So this is not equivalent. So this is not equal. Okay. Now I'll see the same thing, the distribution over global over AND operator. So are they equivalent? So I have globally phi 1 and phi 2, and then globally phi 1 and globally phi 2. So I'm just distributing like this. Now let us take this path pi, which is S1, S2, S3 and S4, and it's continuing S4. and say if I am saying globally phi 1, so that means in every state phi 1 should hold, right, in my infinite path. So phi 1 holds here, phi 1 holds here, phi 1 holds here, phi 1 holds here, right. So that means this path satisfy globally phi 1. Similarly, to satisfy globally phi 2 should hold in all states in that path. So which is the case here, right, phi 2, phi 2, phi 2 and phi 2. So I will say this path phi satisfy globally phi 2. And since this is happening in every state, phi 1 and phi 2 holds, right. So in every state phi 1 and phi 2 holds. So I can say this pi satisfy globally phi 1 and phi 2, right. So what we have seen earlier, this eventual operator does not distribute over AND, right, but global operator actually distribute over AND operator, right. So this implies this also hold. So this is equivalent. So similarly, I will now examine the OR operator and global operator, whether they can, global operator can distribute over the OR operator or not, right. So I am asking whether globally phi 1 or phi 2 imply equivalent to globally phi 1 or globally phi 2, right. So let us see this. So to have this, let us say I want to see this path pi 1, which is S1, S2, S3 and S4. So in here phi 1 holds, this is phi 2 holds, phi 1 holds, phi 2 holds, right. So to have this path satisfying globally phi 1 or phi 2, what you have to do, in every state either phi 1 should hold or phi 2 should hold, right. So in my case, in every state either phi 1 is holding or phi 2 is holding. So I can say that this path pi satisfy phi 1 and phi 1 or phi 2, right, because globally phi 1 or phi 2 means in every state phi 1 or phi 2 should hold. That means either phi 1 holds or phi 2 holds, right, or maybe both also holds. Now let us check for this. To have this path satisfying globally phi 1, you have to phi 1 should hold in every state, but which is not the case here, right. So some state only phi 1 holds. So that means this path phi does not satisfy globally phi 1. Similarly, this path does not satisfy globally phi 2, because to satisfy globally phi 2 in this state, the phi 2 has to hold in every state, right, which is not the case in this case. So this does not equivalent, right. So globally phi 1 or phi 2 hold does not mean globally phi 1 or globally phi 2 should hold, right. So they are not equivalent. Okay. So let us move on. So this F and G are actually dual, right. What is my dual? I can basically write, if I take the negation of this one of the formula which is in terms of F, I'll get G and vice versa, right. So let us see here. So if I take negation of globally phi, which is basically F of not phi. So what does this mean? Let us see. So if I say globally phi, that means I have some path, in the path every state phi holds, but now it is not of globally phi. So that means it is not the case that in every state phi should hold. That means there are some state where not phi holds, right. So you can think about phi holds here, phi holds here, phi does not holds here, phi holds here, and so on. And phi does not hold means not of phi holds, right. So whenever we usually write only the positive part, what are the things holds, rest of the things negation is holding there, right. So now for this path pi, this pi does not satisfy globally phi, right, that does not satisfy globally phi, because to phi satisfy globally phi every state has to have phi, but it is not the case. Or I can write this pi satisfy negation of globally phi, right. I can just does not satisfy means it satisfies negation of the formula, right. Now since in this path phi is not holding in every state, that means there are some state in future where not of phi holds, right, which is the case here. So what I can say in this case, this pi satisfy future of not phi, because in this path in some state in future where not of phi holds, right. So that means what I can write, that not of G phi equivalent to F of not phi. Okay. Similarly, I can take the other one, which is not of f phi, which is similar. I can write this. So let me explain that. So now to have this, let's say I am taking another path here, and so on. So here I am saying that to have in future phi holds, that means there will be some state where phi holds, right? So there will be some state where phi holds, but that is not the case, right? So because it is negation of that, so that means it is the case that in all state not of phi holds, right? So here not of phi holds, not of phi holds here, 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 and so on. So every state negation of the phi holds, right? Otherwise, if at least one state where phi holds, then I will say f of phi holds, right? But this is not the case, so this is not the case. So this has to be the case for pi, right? So in this pi, I would say this pi satisfy f of not phi. And you can see that here in every state not of phi holds. So I can also write that this pi satisfy globally not phi. Globally not phi here, and in this case, because in this state this f of phi does not satisfy, I will write f does not satisfy phi, right? So I'll probably rewrite this. I'll say that because in this state phi does not hold in any future state, I'll say this pi does not satisfy f of phi, or I would say this pi does not satisfy not of f phi. And I have already mentioned this is this pi satisfies g of not phi. So negation of so not of f phi equivalent to g of not phi. Does it make sense? Because I'll just repeat this if you have any confusion. So I'm saying that this path does not satisfy f. That means in there is no future state where phi holds. It means in every state not of phi holds, right? So it means that pi does not satisfy f of phi, which means pi satisfy not of f phi. And since every state not of phi holds, I can say that pi satisfy globally not phi. So this equivalent to this, right? This is what it is stated. So this is simple. You can just think and you'll understand. So this is very important to note what is adequate set. So we have already talked about 4 temporal operator, right? So we have x, u, f and g temporal operator, and you have Boolean operator and, or, implication and not, right? So what I am saying, I don't need all the operator, right? So what I am saying is that if you take u and x, which is sufficient, right? So u and x temporal operator is sufficient or adequate, and similarly and or is adequate, which is you already know, right? I can represent any Boolean formula only using and or, right? So the propositional operator and probably not also I'll put add, right? And this temporal operator only u and x is sufficient until and next operator. What does it mean? It means I can represent this future and global operator using u and x. Okay. So we'll see how I can represent future using until or x. So what I can say, this future in future phi holds means everything is hold, the true holds until phi holds, right? Effectively you are saying that there is a path in which in some future state phi holds, right? So in this is my path, that means everything is holding here. So that means true holds here, true holds here, true holds here until phi holds, right? So this is equivalent. Similarly, if I try to represent globally phi, it means if I take that double negation, it means negation of global phi, right? And then this negation of global phi, the dual I have already discussed in the previous slide. Negation of global phi is basically f of not phi. So I can write this is f of not phi. And now if I take negation, I already know f of phi is, I can represent using true until. So I'll just write this as true until not phi, right? So effectively g of phi equivalent to not of true until not of phi, right? So that means I am able to represent both g and f using until, and x is mandatory. I cannot represent that using until or any other operator, right? So what I am saying that just having u and until and x is sufficient or adequate, I do not need the other operator. But now the question is, why do we need to identify this adequate set? Because when you write the algorithm, we will discuss how to identify the model checking algorithm, right. So given a formula, when you write in terms of this temporal operator, how do you check in a model, right? So that model checking algorithm, I don't need to define algorithm for all 4 scenarios, right? Now I can only define algorithm for until and next operator, which is sufficient. I don't need to identify algorithm for f and g operator, right? So this adequate set is basically is useful in that context, that even if I have a formula which is written in terms of f and g, I can convert them into until or x, and then I use the algorithm for x and until, right, the next and until operator. Using that algorithm also I can verify the property which is written in terms of f and g. So that's why this adequate set is important. Okay, and the Boolean operator we already know how I can write implication in terms of and or and so on, right? Okay, so this adequate set is important. Now this is another important point to note here, that what kind of formula cannot be represented in LTL. Okay, this is also very important. So to answer this question, you recollect what we have said, that some model or some Kripke structure satisfy a formula f. When we say that this formula satisfy f, it means all paths starting from the start state of that model satisfy form, right? So from the start state there may be many paths, right? There may be many paths. All paths should satisfy this formula starting from the start state. Okay. So now, so that means it's basically by implied any formula means in all path, right? Whenever I am saying that this particular model or Kripke structure satisfy a formula, it inherently implied all paths starting from the start state should satisfy this. So this is, that is by default the formula is kind of checking in all path, right? Now if I try to identify some formula where I have to check in some path, there exists some path in which is happening. Can I represent in LTL? Ideally, because the LTL algorithm will check in all path, but I want to check in some path, or there exists at least a path, right? So in general I will not able to check it, because I by default the LTL will check in all path, right? But you think about, if I take a negation of this, the formula, which will means the all path, right? Some path, so I am saying this formula holds in a path, some path, it means the negation of the formula should hold in all path, right? So take the negation and I will check whether this formula satisfy the negation of the formula, right? Because there exists complement is for all, right? So that means even if your formula need to find out in there exists a path, I can take the negation of the formula and I will try to check whether there is all paths satisfying that formula or not, negation of the formula. If it is not, then I will say the original formula is satisfied, right? So this way, if you also have there exists, I can represent. Then what we cannot do? I am doing both, right? For all and there exist, right? But if you think about a formula that needs both, right? So you need both for all and there exist. Those kind of formula, even if you take negation, you cannot represent, right? So the property that need to satisfy both for all and there exist cannot be represented in LTL. To give an example, I am saying if from all states there exists a path. That means I am trying to see for all state there exists a path. That means it's basically take care of it consists of both for all and there exist. Even if you take the negation, this will become for all and this will become there exist, right? So I will not able to check the negation of the formula also by LTL. So this kind of property cannot be represented in LTL. Okay. Let's move on. So there are two more operators I will quickly introduce, which is called weak until and the other one is called release. So this also being used, I would say some less used operator in LTL, but let's we should know what this operator means, right? So weak until is something a weaker version of the until operator. So if you recollect, to satisfy this until, you have to think about a path which is say S1, S2, S3 and infinite path. I'll say this path satisfy phi 1 until phi 2, what is happening? Phi 1 holds until phi 2 holds, right? So that means, let's say some state where phi 2 holds, let's say in S4, until all the state phi 1 holds, right? Phi 1 holds. So that means for there exists some j state, right, which is greater than or equal to 1, where this pi of j satisfy phi 2, and for all I which is 1 to j minus 1, so till the previous state, pi of I satisfy phi 1, right? This is mathematical or formally. In weak until, this is the first part, right? So this is basically the until part, where I am saying there exists some I, let's say if I try to, there exists some j such that pi of j satisfy phi 2, I try to sync with this, right? And for all I which is from 1 to j minus 1, pi of I satisfy phi 1, right? So basically this is the until part, right? Or I am saying that in all state only phi 1 holds, right? In for until, you have to have phi 2 hold somewhere, but in addition in weak until, I am saying this, if you have a state like S1, S2, S3 and so on, I am saying only phi 1s keep holding, right? Phi 1 and so on. So if phi 1 keep holding, then also for all k, pi k holds phi 1, right? So weak until operator takes until plus an a special scenario where only phi 1 holds. For until operator, you have to have some state in future where phi 2 has to hold. If phi 1 keep holding, I will not say this path satisfy phi 1 and phi 1 until phi 2. But in weak until, you may have either phi 1 and until phi 2 holds, or only phi 1 keep holding, right? So that's all. So what is the equivalence? If I say phi 1 until phi 2, that means this is weak until plus in future phi 2 has to hold, right? This is actually excluding these scenarios, right? So this makes sure that only this scenario is happening, okay? So this equivalence is well understood. So some examples are here. So you have say 4 state phi 1, phi 2, phi 1, phi 2, this is holding like this. So I can say that this pi satisfy phi 1 until phi 2, right? Because phi 1 is holding until phi 2. After that I don't care, right? Does this states also weak until? Because weak until is union of this plus something. So I will also say this pi satisfy phi 1 weak until phi 2. Now let's think about a state here where only phi 2, phi 2, phi 2 holds, right? So does this state satisfy phi 1 until phi 2? Answer yes, because I am saying this phi 1 holds until phi 2 holds. But if you see the definition here, it starts from the first state itself. So it may be happen that in first state itself phi 2 holds, right? So this path also phi satisfy phi 1 until phi 2, and by virtue this path also satisfy phi 1 weak until phi 2, because whenever phi 1 until phi 2 holds, weak until also holds, right? Now take this path where phi 1, phi 1, phi 1, phi 1 keep holding phi 1, right? So this path, as I have already discussed, does not satisfy phi 1 until phi 2, but this path satisfy phi 1 weak until phi 2 because of the second part of the clauses, right? So here, if even if this path only satisfying phi 1, I will say pi satisfy phi 1 weak until phi 2, okay? Yeah. So similarly, the release operator is just the opposite sense, right? So here I am saying if phi 1 until phi 2 means phi 1 keep holding until phi 2 holds. Here it is release, that means phi 1 release phi 2, that means phi 2 is holding and until phi 1 is coming, right? So it basically release phi 1 release phi 2. So that means you have the states, right? You have the state S1, S2, S3 and so on, S4. So phi 1 release phi 2, that means phi 2 is holding here, phi 2 is holding here, phi 2 is holding here, and then in this state phi 1 and phi 2 both holds. See the definition. What I am saying that there exists some I such that phi I where phi I phi 1 holds. So that is say S4, right. So in S4 state phi 1 holds, right, phi 1 holds, and for all j from 1 to I, it is not I minus 1. If you you see here it was till I minus 1, right. So that means the state where phi 2 holds, phi 1 should hold till the previous state. It may be that in the state phi 1 and phi 2 both holds, but I don't care about that, right. So it has to hold till the previous state, but in release it has to hold, both of them should hold here, because j 1 to I pi j equal to phi 2. What I am saying that all state till the ith state phi 2 holds, that means including the current state, right, and uh, in that ith state phi 1 holds. So that means phi 2 is releasing phi 1, but both are holding in this particular state. Or it may be the case that only phi 2 is holding, right. So you can have the state like this where only phi 2 is keep holding, right, phi 2, phi 2, phi 2, and phi 1 never holds. But the difference here in release that phi 1 and phi 2 both has to hold in a particular state, whereas in this case it is not necessary. It is basically you have to make sure that till previous state phi 1 holds, and in the particular state in ith state phi 2 holds, right. So this is the difference between these two. So again let us take an example. So here phi 2, phi 2, phi 2 holds, and then here both phi 1 and phi 2 holds, then I will say phi 1 releases phi 2, right. So this pi satisfy this. Similarly here phi 2, phi 2, phi 2, is phi 2 keep holding, then also I will say pi satisfy phi 1 releases phi 2, because it is never releasing, right, just keep fighting. So that is the second part. So these are the two scenario where this phi 1 release, phi 2 holds, okay. So now there are equivalence between this weak until release and until. This I have already discussed. This phi 1 until phi 2 means either weak until, but you have to make sure that phi 2 holds in future. Similarly, phi 1 weak until phi 2 means either this hold or globally phi 1 holds, right. You remember that in weak until you can only phi 1 keep holding, right. So that is that scenario. Either you have the this scenario, this is until, or this scenario, right. So this is what I wrote here. Similarly, I can write this weak until and release. So I am saying phi 1 weak until phi 2 means phi 2 is releasing phi 1 or phi 2. Why phi 1 or phi 2? Because in this case you have the scenario. So phi 1 weak until phi 2 means phi 1 is holding phi 1, phi 1, phi 1, and then some states say phi 2, right. But phi 2, that means phi 2 is releasing phi 1, but in that case you should also have phi 1 holds, but this is not the case. This is not necessary for weak until. So that's just for completeness I also add phi 1 or phi 2, so that this holds here, right, because phi 2 holds means phi 1 or phi 2 holds. This is I am keeping for, because there is another scenario where you can only phi 1 keep holding, right, and phi 2 never holds. So that's why I just keep phi 1 also here, not only phi 2, okay. So similarly phi 1 release phi 2 means phi 2 weak until phi 1 and phi 2. Let us understand this, because if you are releasing this, right, so if you remember in release both has to hold some state, right. So I am saying this phi 1 releases phi 2, so that means phi 2, phi 2, phi 2 holds, and then in this state phi 1 and phi 2 both holds. So then only this scenario true, right. So that means what I am saying is phi 2 holds until phi 1 and phi 2 holds, right, weak until. And I am just keeping this because it may be because only phi 2 keep holding, right, that is the another scenario. So that's why this release and weak until get connected for that scenario, okay. Similarly, I can identify the equivalence between until and release. So they are effectively dual, right. So what I am saying, if I take a negation of this until, then I will get this. So let us understand this. So when phi 1 until phi 2 holds, so basically phi 1, phi 1, phi 1, and some state phi 2 holds, right. and when this holds, I am saying that not phi 1 releases not phi 2. That means not phi 1, not phi 2, not phi 2, not phi 2 is happening, and in some state not phi 1 and not phi 2 both are holding. So this is basically the state path which satisfy not of phi 1 releases not of phi 2, right? Now you see here, whenever I am saying here I am not saying anything, I can, so not of phi 1 is not holding, I can say phi 1 who is holding, phi 1 is holding, phi 1 is holding, because I am not saying not of phi 1, and in this state phi 1 is not holding, right? So what I can say here, that in this state I am getting phi 1, phi 1, phi 1, but I do not get phi 2, I am getting not of phi 2, right? So that means in this path phi 1 and phi 2 is not holding, right? So I can say this path, I am just taking this path which satisfy not of phi 1 until phi 2, right? So which is basically this case. So this negation of phi 1 until phi 2 means not of phi 1 release not of phi 2, and similarly I can get the other two. So if you take a negation of the release, I will get not of phi 1 until not of phi 2. Okay. So I hope this is understood. Now what I will do, I will take very simple example from hardware design and try to encode them quickly, right? So say, let's say this mutual exclusion in bus arbitration, two masters should never use the bus simultaneously, right? So if there are two masters, you have a bus where it is shared by two masters or two unit, they cannot use together. This I have already talked about. This is basically mutual exclusion. So if M1 is the one master and M2 is the other master, so I will say M1 use and M2 use cannot happen together. So globally not of M1 use and M2 use. So this is I have already discussed earlier. Let's say I am saying if you request something, it will eventually be granted, right? You think about you are requesting some resource, it has to eventually get granted, right? So it means if you are requesting, in future grants would come, and this is globally true. Okay, makes sense? And this is something common in arbiter and NOC router, this kind of property. So this is something no spurious grant. That means grant cannot occur without a request. So you will get grant only if you request, right? So if you have grant, then only you will get a request, and this is globally true. So this is basically to avoid invalid resource allocation. It means you are not requesting, but you are still getting the grant, right? So to avoid this in some NOC arbiter or any other cases, right? Let's say FIFO behavior, where you basically have a FIFO where you can first in and first out option. So if somebody is writing here, somebody is reading from here, but you have to make sure that when you are writing, it must not be full, right? You can only write when there is not full, and you can only read when it is not empty, right? So this is the FIFO property. So we have to make sure that if I write this in LTL, how do you write? So so I am saying that writing is prohibited or cannot be done when FIFO is full. That means full means not write, and it is globally true, right? So it basically prevents buffer overflow in FIFO writing. Similarly, if I try to take that reading cannot happen when FIFO is empty. So that means empty means not read, and it is globally true. So again, this is to prevent invalid read from a FIFO operation. And this FIFO is a very common block in hardware design, right? So when you use some FIFO, you have to add all this property. Let's say I try to say ki grant must be arrive in next cycle, right? Means if you request, in the next cycle grant should come, and that is globally true, right? So this is something if you have some meaning that arbiter must respond within one clock cycle. So you can encode that particular thing using this. Say pipeline hazard detection. So what I am saying, that pipeline must stall after hazard. So you know pipeline hardware, right? And you want to make sure that whenever there is a hazard, it may be data hazard or control hazard, the pipeline should stall. We can just add a property like if there is a hazard in the next state, it should be stall, should be 1, right? And that is globally true. So this will ensure that you do not have any incorrect instruction execution in pipeline architecture, right? Handshake protocol, when there are two modules sending some data request and acknowledgement, what I am saying that every request eventually be acknowledged. It means if request means in future acknowledge should come, and that is globally true. So this is basically reliable communication when you are communicating asynchronously between two modules using these signals. Okay. So traffic light, you have basically a crossing like this, right? East, west, north, south. So if you give green signal here, say it's coming from this north to south, and if you give green signal here, so then traffic should come here. This is east to west. I'm just encoding that part. You can identify the other combination as well, right? So what I'm saying that eventually you cannot give both this green signal together, then there will be a collision, right? So both direction cannot remain green simultaneously, which is very obvious. So green north to south in this direction, green east to west, both cannot be true together. So negation of this should be true globally, right? So this is basically prevent traffic collision. Similarly, you can think about south to north and west to east, south to north, east to east. So there are all possible combinations. You have to write property like this. Okay. Similarly, if I write, see, north to sign green eventually changes, right? You cannot just give one direction on, right? So I'm saying green north to site in future, green east to west, right? So I'm basically saying that this stop and this become green in future, and that basically fairness in this traffic monitoring. In RAM, SD RAM, you can think about that read operation waits until activation, right? So that means until until you get it activated, you should not read from this. So not of read until activate, and this is globally true, right? Demonstrate the use of until operator, and this is basically disable the until activation. Read remain disabled until activation occur. Few more. Processor reset recovery. Here I am saying that processor eventually reaches idle state after reset. That means if reset, eventually in future idle state will come. Okay. No deadlock in NOC router. I am saying that if some packet comes into the arbiter, it should eventually go out. Otherwise, it's a deadlock, right? It is not moving. So that means that some packet in a arbiter, in a router, the packet out must be true in future. So globally, this must hold to make sure that there is no deadlock in your NOC router, and this is true for every arbiter or every packet in possibility in a router. Persistent request property, here saying the request remain active until grant arrives, right? So request means request remain true until grant arrives, right? So it basically saying that you just make a request and keep it on until you get your grant, right? And eventually stable clock is in future globally clock is stable, right? So this is eventually globally clock is stable. So with this we conclude today's class. Just to summarize what we have discussed today is we identify many properties in LTL. What of them are equivalent. We also identify the this adequate set for LTL. We also identify the new two operator, weak until and release, and their relation with until operator. And then we have taken very few, quite few examples from hardware design and see what will be their LTL encoding, right? With this, I conclude today's class. Thank you.